Hello and welcome. My name is Luciano Lucas. I'm the Executive Vice President here at VR Vision, and today I'm giving this brief presentation on the new features from 8.8, Aivia 8.8. The format of the presentation is a little bit different following some of the feedback from you and some of our collaborators. We will have, instead of a long presentation with a lot of theory, we won't do that. We will have a briefer introduction which will cover the key features, followed by a series of demonstrations. We have done a number of webinars before that cover the basics of machine learning and deep learning, as well as how we use those for both image segmentation, restoration, and prediction. So you're very welcome to watch those videos. They're on our YouTube page as well as our homepage. So let me introduce you to the key features from Aivia 8.8. We've invested in two specific parts of our toolset. One is the Aivia Cloud, which is our tool for training and applying deep learning models. And it doesn't require any coding experience. All you need to have is your training data, and we have an infrastructure for you to train and apply models. We've done a lot of work there, and I'll tell you a little bit about that. We've also implemented a lot of new features into our pixel classifier. This is our tool for segmenting images using parameter-free approach. So let's start with the pixel classifier. The pixel classifier previously was implemented to run on the CPU, which in many cases was sufficiently fast, but we found that for larger datasets or datasets that required a 3D version of the feature that was needed to process the image, then it was a little bit slow. So because of that, we've implemented most of the features, and especially the ones that are computationally most expensive, onto a GPU implementation. That means that in worst case scenario, your images will now run twice as fast. And in many cases, it's above 50 times faster, even 100 times faster is possible if you're using some of the more complex 3D features that we offer. Now, all that means is you can do this faster. You can teach and you can apply your pixel classifier a lot faster, which means you can process larger images than you could before. So this is one part, the GPU implementation. We've also added a number of new features to annotate. Previously, we had just a paintbrush. Now we have a magic wand based on flood filling algorithm. And we've ported the tool that a lot of you told us that you like from the contour editor, which is optical flow algorithm. We ported it from the contour editor into the pixel classifier so that you can paint in one Z slice and it predicts the next Z slice for you. The magic wand works in 2D and in 3D, and it helps you train much faster. So it can predict also multiple slices. So you have these two options to paint in 3D that are a lot faster than the previous option, which required you to paint every single Z slice by hand. In addition to those that I've mentioned that work primarily in the 2D viewer, we have now a new implementation for the 3D viewer, where you can just click once in an object of interest. You can set a region of interest pretty quickly, and whatever is inside of the preview that you see, which looks like a mesh surface, becomes foreground, trained for the want class. And whatever is outside of that mesh, but inside of the bounding box of that region, becomes background. So in a single click, you can train the background and the foreground in 3D, and that is fed into the pixel classifier pipeline. So all of these annotation tools will help you train a lot faster, so annotate a lot faster than you would otherwise, especially if you're doing this for 3D images. The third part of the pixel classifier, or the third feature of the pixel classifier that we are introducing today, is the possibility to train on multiple images and train over multiple sessions. That means you can save off a session with the annotations, the images, and the classifier that you are training up to, let's say, today. And tomorrow you can open everything up, add more images, even edit the annotations you've made in previous days, and continue to make your model better and better and better. This previously wasn't possible. You had to basically train everything in one session, and that classifier was a monolithic classifier. From now on, you can load classifiers, edit them, add new training, and continue making them better and better. So these are the key features for the pixel classifier, and I'll move on to the Aivia Cloud related features. Aivia Cloud was launched about a year ago, and since then we've been working to bring that application from a standalone application, which is what it was, to an application that runs within Aivia itself. There's quite a few benefits related to that, and I'll mention a few of the things that we've already done, and we'll be doing even more in the future. So first thing you'll notice is you don't need to make 2 installations. It's just you install Aivia and it comes with Aivia Cloud if you have a license for it, obviously. The next thing is there is now a local mode, which means you can run your Aivia Cloud software, which allows you to train and apply deep learning models on your local computer. And you can do that also on a computer that has multiple GPUs, and you can specify how many GPUs you want to use locally. So there is no need to upload data to the cloud anymore. So that's one part. You have local apply with multiple GPUs. The second is that now we do quite a few tests before you use the data for training a model. We check, for example, if the resolution is the same between your raw data and your ground truth. We check if the bit depth is the same, if the dimensions are all correct, so the XYZ dimensions, if there's a number of channels and so on. So we do a number of checks on the images that you're planning to use for training to ensure that you are successful most of the time, or that you're successful as much as possible with this application. And finally, we've added the possibility to stop the training at any point, and you can collect the last or the best model that is available at that particular moment. So if you're looking at the graphs that show the progress of training, you will see the error going down and the pixel to noise going up. If you're confident that the model is trained well enough, you can stop it and just collect that model and use it in either Aivia Cloud side or directly in Aivia as a drop-in recipe. So those are the 2 main areas that we've invested in for this release in 8.8. In addition to this, we've developed many other features and fixed quite a large number of bugs and fixed performance issues. And thank you very much for everybody's feedback. We appreciate that, and we hope you continue to send that feedback, because it does help us make Aivia even better. So one of the things that you've asked for is Python integration, and this is done now. At least the first implementation of this Python integration is done, which lets you run your own Python scripts. And one of the demonstrations I have later on is exactly on this, is running a Python script that will calculate the quality of an image using the structure similarity index. And that's a Python script that runs in parallel with Aivia and then sends some results back to Aivia that you can display. So that's the first thing, the Python integration. We've also added a number of import and export, generally speaking, import-export functions into Aivia. For example, we can read in CSV and text files to create tracks and 3D spots or 3D points. So if you've created those in MATLAB or elsewhere, you can now import them into Aivia and continue to work with them. We also can read DXF files. These are from Reconstruct software, very popular if you're doing EM tracing of neurons, for example. We can also support now CZI files, and we've done work also on the H5 file format. There's additional features that I'm not mentioning right now, which you can check in our release notes. In addition to the ones I already mentioned, I'd like to just mention one last one, which is we now have a floating license manager or a site license manager. It's a software that we developed ourselves, and it allows you to float a license that you already have of Aivia within a big range, let's say a university department or a whole university. So that is, in a nutshell, what Aivia 8.8 is all about. A lot of functionality on the pixel classifier to help you more quickly, more efficiently train and apply parameter-free image segmentation. And the Aivia Cloud side of things, now it's fully implemented inside Aivia, and it has a few new additional features. And then there's quite a long list of other things that we've done to help you get your job done. In this demonstration, I will illustrate how to segment tentpole ruffling on a single cell. Tentpole ruffling has been described by several, and there is one particular paper I'd recommend, a recent one from November 2018. Nicholas Condon uses a lattice light sheet to image these structures dynamically. They appear as you can see them here, typically on the surface, but sometimes there are internal structures too that lead to this external structure. So we'll try to identify these using the pixel classifier. Start by moving here to 2D, turning on the pixel classifier from the analysis tools tab. By default, I have two classes. I will need three in this case. The actual tentpole right here. Move to a different Z. Okay, the background and the cell itself. Okay, and the preview is already turned on, so you will very briefly see segmentation of this data set. Definitely background here. Okay, so that's looking pretty good already. Let's look around in the different Z position. Let's check here. Seems like we're still getting a little bit, these areas are still being considered to be part of the cell. In fact, they're not. I think that will do the job. There's also some internal structures here that look very similar to the tentpole. So I'll also paint those as well, because I'm interested in getting those included. Okay, I think that is all the training that I will do, and I'll then turn this to segmentation, turn the region of interest first of all, so we can check it out. So I can turn the region of interest here on. So just this part is going to be previewed in 3D. I can come to 3D, and now we should see this as a 3D mesh coming up, as well as a part of the cell being rendered as a 3D mesh. So we're generating a preview right now. Okay, that's done. And you can see the structure has been detected reasonably well. Once the pixel classifier applies to the image, we then have two new object sets, one for the cell and one for the tent pole. And we can see here the tent pole detected where you would expect it. So it's this structure here. So right now I'm showing both the volume rendered data as well. So that's the volume rendered data. We have a 3D object set for the cell, and then another 3D object set for the tent pole. And we can have information for the tent pole, for example. That's this structure here. We know how big it is and its properties. It's also interesting to look from inside, perhaps from the opposite direction. At its contact points with the inside of the cell. And you can see them now. And that is how you would do the segmentation of the tent pole using the pixel classifier. Here is that same data set, and now we'll use the 3D magic wand to do the segmentation using, of course, the magic wand inside the pixel classifier. So start pixel classifier, turn on the magic wand, it turns on by default. Also starts two classes by default when you enter, and then you can annotate in 3D with a single click. So just select a region of interest, paint, and you can come and check if the annotation you've made is reasonable. Looks good. I'll now check different Z position to see if the segmentation is looking reasonable. That's what it looks like already. So that's pretty good. We can, of course, edit this annotation with the magic wand, for example. We can magic wand in 2D. We can further train or train a little bit more material if we want to improve on our result. So that will probably make it a little bit better since there was a little gap there. Now there is no gap, and this training can then be applied to additional Z slices, and the segmentation is what you can see now. So if I go to 3D, it will create a 3D mesh representing this region here. I can then teach this classifier and and apply it on the whole image, or just in this ROI that we predefined around the cell, around the ruffle. So I'll apply here, and this will create a new object group up here. Okay, that is complete. You can now turn off the channel to check what that looks like. You can also inspect it using the ortho slicer, for example, and you can see here the outline. It's pretty accurate considering the amount of training material that we've used. Here you can have an idea of where we are. So I'm going up and down and showing a section of the mesh that we generated. Here shows just cross section of both thick slice actually, and this is the whole ruffle in this region. With this little amount of training, we did manage to get the tent pole. We did get a few other things out here that are perhaps not of interest, but with a little bit more training, this would get very, very accurate. And because we have this pixel classifier, we can save it off and apply it to other images, even a time lapse, in case we wanted to detect more of these structures over time in other samples. And here is a sample from Adam Tyson at King's College in London, UK. This is a cleared sample and then imaged on a Zeiss multiphoton microscope. It shows both axons and cell bodies, and we'll try to do some segmentation of the structures that are visible here using the pixel classifier in 2D space. So I also want to illustrate how the ROIs work and what that looks like in 3D when we are painting. So I'll start by defining or creating a new classifier. So it by default creates one with 2 channels. I don't want to create an output for the background, just for the want. And I'll go ahead and draw a few examples of cells. Until 8.5, the only tools we had were these that allowed you to paint like this, and then you can paint the background as well. This is fine if you have just a single slice, but if you want to paint multiple slices quickly, this isn't a very good way to do it. So we now have additional tools to paint in 3D. So for example, one of the tools is the magic one in 2D, and you can place it on top of a cell like this, increase the sensitivity, and it will fill all of the cell. And you can choose to paint multiple Z slices, and that will paint all of those slices of that cell. Let me just change this to a darker color so we can see that a little bit more clearly. So that is an annotation created there. I can move to a different area and paint a different cell, and perhaps this one as well. So a few examples of foreground. I can also paint the background in the same way. Okay, and now I can output in this case these are cells as a confidence map. That's what you see in dark blue. And I'm doing a region of interest here. I could change the region of interest to here, and now it's going to show me that area. It looks like we're still detecting a little bit too much of the cells, so I can adjust by painting a little bit more background in the area, and it's going to adjust. It's generating the preview, and now it's updated. I'm interested in a segmentation map, not just a confidence map. So if I changed it to confidence to segmentation, now I have a segmentation map into the space. If I go to 3D now, it will compute a 3D mesh for those cells in that region. And you can see them right here. So I can turn that off. And I'll turn them back on. Takes a moment to recompute. So that's those cells that we were just looking at. If I want a permanent result, then I have to teach this classifier, which now, because it's GPU implemented, it trains very fast. And then I can apply it also in that ROI that you just saw there. Both the GPU implementation and the ROI apply are features from Aivia 8.8, which are very handy if you have a large data set that you need to work through. Okay, so this is an ROI that we've done. If I don't want to apply in an ROI, I can turn the ROI off, apply again, and it's now going to apply this pixel classifier that I just trained to the whole image. So, okay, the analysis as completed, and we now have fully segmented nuclei in this data set. We can, of course, go into charts and explore it a little bit more. Look at the highly spherical objects over here, or the least spherical, probably the ones that need a little bit of attention in terms of partitioning. That's the ones up there. In terms of the spreadsheet, we have full access to the parameters here, and the object sets that are here can now be color-coded with any parameter of interest. That's, for example, the average intensity on the green channel, but we could use sphericity. That's the one we were just looking at a moment ago, and that's how it would look like. Can quickly adjust the colors here if you like, to have a different spread of the color map. It's very handy, very handy way to do that. Or just change the color map over here. Okay, so that is how to apply or train a pixel classifier, apply it and preview it first of all in ROI, and then apply it in an ROI, and then finally apply it to the whole image. And we've used both the original tools, just a paintbrush, as well as the flood filling magic wand tool in 2D, which paints in 3D but annotates in 2D. One additional note about what you can save and reload into the Aivia 8.8 pixel classifier. The annotations that we created can be saved off through this menu here, and that will save the PX annotation. So these are the annotations for this particular image. That's the annotations we made by hand. It's also possible to save the classifier, so you can apply it to other images, and you can save off all of the training fields, so all of the images that you've used, because you can do multi-session, multi-image training. You can save off all the images together with the annotations to a single location on your disk. That is the most handy way to keep track of all of your information, but of course it also creates a lot of data. One final note, the pixel classifier can be batch processed here, so you can batch apply a pre-trained classifier on multiple images, and that happens through this menu down at the bottom here. In this demonstration, I will show a couple of things. First, how to apply a pre-trained deep learning model created in Aivia Cloud, and then how to check the quality of the image restoration that we've achieved. And we will do that using one of the new features of Aivia 8.8, which is the Python integration, which allows us to run a script written by Patrice Mascalchi from the team based in Europe. So in this dataset was created with SP8 with the resonance scanner, and it shows some labeled neurons. Dataset was created by Hu Zhao at Texas A&M, and dataset, the input data is relatively noisy, as you can see, because it's a single scan. The ground truth data is substantially better, and that is composed of images created with 49 average scans, so 49 or 48 scans that were then averaged, and that's what you get here. So much higher quality image as the ground truth. And that image was also deconvolved, the ground truth image, whereas the raw data was not deconvolved, and it's a single scan. So we've trained the model, as I mentioned, and now I'm going to apply that model. Here is the model, so I can drop it into Aivia. It will create a recipe. I choose the raw input. I can set a region of interest if I want to run this quickly, or I can just run it on the whole image, and that's what I will be doing. So input the raw image. I'll run it on the whole data set. Let me show you what that looks like. So when you start it, it will take a little bit of your GPU dedicated memory. I'm using the RTX 2080 in my laptop, and then the CUDA will speed up and get to nearly 100% over here while the image is being processed. When it does complete, you will see a note on the bottom of your screen here indicating that Aivia has finished processing that image. So the result is this channel over here, and that's what the result looks like. So that's the raw input. That's what we're getting by applying our pre-trained model, and this is the ground truth. So certainly a huge improvement versus the raw data to get to this, but perhaps not as good as the ground truth. And that's really what I wanted to check now. So we have, as I mentioned, the possibility to now write your own Python script. This is one written by Patrice in our team based in Europe. And you can see his script here. And so this script is ready to go. All I have to do is drop it into Aivia. That's the same one we were just looking at. So I'll drop it in here. It will create a recipe, and I can take ground truth is the ground truth. Restored is my result, and I'm going to run that. Okay, that's complete. You can now have a look at the result here. So let me turn this off. So it helps to have a color map that is a little bit more indicative. So rainbow 1 is good. So if it's a very low intensity value, it means low confidence or high disagreement. So this is low quality. Everywhere you see these kind of colors, and red more specifically indicates that there is disagreement between ground truth and the reconstruction. But generally it's in the blues and greens, which means there's a big agreement between the two images, between the ground truth and the restoration. So this would illustrate an area down here in this area. So this area here is probably where there is most disagreement, and we can check that. So I can now turn on, that's my result, and this is the ground truth. So in this area, this Python script identifies that there is significant disagreement, whereas in other areas, let's see up here, there is less of that disagreement. So this is the ground truth. Oh, sorry, this is the result, and this is the ground truth. So this is a higher quality restoration versus what you saw at the bottom. Okay, now that we run it for a comparison between the ground truth and the result, and I'll just rename this so that we know what we've done with this one. Now I'll run the same analysis, but instead of the result, I'm going to compare it to the raw data and run. Okay, it has completed. So let's have a look. This is the new one, SSIM image. I'll do the same exercise, just change here the lookup table to the same one I used before, and change the name. Okay, And you can straight away see that most of the pixels on this image indicate high disagreement between ground truth and raw data. So just for comparison, this is ground truth versus result, this result or restoration, and this is ground truth versus the raw data. So versus the restoration versus the raw data. And it's no surprise considering the raw data looks like this and the ground truth looks like this. Okay, so that's the exercise that I wanted to run. So a couple of things: apply a pre-trained model and then check quality using a Python script that integrates now into the Aivia platform. In collaboration with Harish Ruff, Gigi Chen, Chris Combs, Alex Zovmer from the NIH, we continue to explore how deep learning can be used to denoise and restore images. Here is an example of a recent experiment that we did where we took STED data and confocal data from the same field of view for two different subcellular compartments, the nuclear pores and microtubules. So the confocal data looks like this. You can see this is a part of our training data set. It's pretty good confocal data set. The ground truth STED looks like this. So much higher resolution as you would expect. So this is just for the nuclear pore. This is the confocal. This is the real STED. And for the microtubules, this is confocal, and this is the real STED. Then we trained the model with these pairs of images, raw and ground truth, so real STED and confocal. And with that, we can go from now we can go from raw data that looks like this to restored that looks like this. For comparison, that's what the ground truth or the real STED looks like. This is what the restored image looks like. So from raw, we go to restored. Pretty exciting results. Of course, these are preliminary results, but nevertheless worth mentioning. In terms of the microtubules, this is the raw input, and this is our result, so the restored result. And for comparison, this is the ground truth STED data. So pretty close. Not certainly not perfect yet. We continue to work on this problem, but we are excited by these initial results to go from raw data that looks like that to restored data. So this is a deep learning restored image that you're looking at right now, based on the STED data that we acquired. So in addition to this, we've also done a little bit of work using just STED data. So in this case, we have STED at ultra low signal to noise. So that's what it looks like here. And this is the, let's say, high signal to noise STED data. Of course, a lot more energy was used, a lot more laser light was used to create this image in comparison to this image. And then we can restore from an image like this, we can get to an image that looks like this using the pre-trained model that we've created. So that's the improvement. So from this input, we can achieve this output for the nuclear pore. And for the microtubules, the input data looks like this. The ground truth data looks like that. and the restored is what you can see now. So from an input like this, we can get to a restored image that looks like this. The type of model that we're using is an Arcan, and we have been testing and evolving this approach for more than a year now, year and a half, 2 years, and we continue to do research work in this field, and we'll continue to do that. And when it's in a good state, we will deploy a pre-trained model so that you can also either convert confocal data to STED like data, like I showed you before, or if you're doing STED and you want to use lower light conditions, which would typically create high signal-to-noise images, low signal-to-noise images like this, so that you can convert images that look like this to higher quality images that look like that. I'd like to thank our collaborators for their input, advice, and motivation. It's a pleasure to work with all of them, and I'm looking forward to continuing our joint work in the coming months and years. And here is the Aivia team. This is my team. I'm very happy to work with all of them. On the top row, so first, second, and third row, all the way to Gaoyu, who is our newest algorithm engineer, is everybody that works on the software and algorithm development. Beyond Gaoyu, Svagata, Quinn, Hoyen, Patrice, Trevor, and Jim, all of them are customer facing, and the last three specifically are our applications and sales specialists. It's a pleasure to work with all of them, building the tool, testing the tool, and then bringing it to you and providing support for your specific applications. I'm looking forward to continuing to work with this team and with all of you listening to this presentation now. In the coming weeks and months, we'll be attending a number of events. We have a couple of workshops, one in Cambridge, another one in Paris. We're attending a conference in Nantes, and attending also ASCB EMBO in DC, Washington DC, at the end of the year, so 7th to the 9th of December. If you want to try Aivia 8.8, you're very welcome to go to the website /demo. You can also find it on the top right of the website and request a demo license for you to try out. If you already have a license, then you will get some information on how to download Aivia 8.8, so you can start to use it straight away. We do provide support locally, but also by email. In Europe, you can count on Patrice. East Coast and South US is Trevor. Then Jim Palladino is on the West Coast. And nearly every day of the week, we run online image analysis clinics, and you can check it out on our Twitter account. Is where we normally announce the times and the location, and you can join the private web meeting room and ask any question about image analysis and image visualization, regardless of the tool that you're using. So in conclusion, today we talked about Aivia 8.8, which includes a much faster and more versatile pixel classifier. We introduced Aivia Cloud 2.0, a year on from the first version, and a first integration of Python scripting, so you can run your own Python code in parallel with Aivia. Thank you very much for attending the Aivia 8.8 webinar. I hope you enjoyed it, and if you have any questions, we'd be happy to answer them now. Hi, hopefully you can hear us. I see a few questions coming in. With me is Casey, here, and Mike, who you've met before in the previous presentation about the pixel classifier. Casey actually does a lot of the work on the pixel classifier from the start, and that's why he's joining me as well here today for answering any questions that might come up. And Mike, as you know, is the guy on the machine learning side of things that has prepared the algorithms and the infrastructure for us to have the pixel classifier. So I see a few questions here. The first one comes from Jeremy Cheng, and it's about which Python libraries are supported. This is actually a very good question for another person that is here. John is also on the team, and he's the one working on the Python implementation and also on Aivia Cloud. So he's right here. I'm going to move over and let John answer this one.
So by default, NumPy and skimage are installed. Once Aivia is installed and Python is installed, you're more than welcome to add any imports or in pip install any modules that you'd like to use. There's no restrictions once you're in Python in terms of what you would like to use or what restrictions there are or anything like that. It's a standard dev Python environment, so use whatever you like.
Great, thank you. Okay. Thank you. So if other questions come up, so the three of us are here just because we fit three people, but if more questions come up, there's actually, most of the development team is right here. So the next question comes from Alex Carise. Hi guys, great talk. Is the train model dependent on pixel, size, objective, other image parameter, or is it applicable to multiple imaging modalities once trained? Typically, this is the case is the second answer, but maybe Mike can expand a little bit if you like.
So typically it works best if it's on the same modality, but if the modalities are similar enough, it will work fine. It's easy now to test by adding different training images to and you can see before and after if it's going to be working.
Yeah, and we have examples actually. Recently, the demo I did a moment ago with the STED data, it had microtubules and nuclear pores. The data was actually, the model was a single model trained with both data sets. It had the nuclear pore and the microtubules all trained into a single model, and we could restore for both. So for that one, it's a single model that does both organelles. But if you did change to a totally different modality, let's say if you went from STED to, I don't know, wide field, that model wouldn't work well. Okay, so there is some dependency, but yeah, depends also on what training data you have available. Okay, the next question, that's kind of a, yeah, thank you from the Calico Labs in San Francisco. And with what is the icon left of the magic wand? Oh, in the pixel classifier. Oh, that's a great one.
The auto contour tool.
Yep.
That's you draw a region and it uses optical flow to try to extrapolate what the next drawing for the next frame is going to be. Can you explain optical flow a little bit if they don't already know what it is?
So the version of optical flow is trying to predict per each voxel location what is going to be the next voxel location in the next slice. So it's kind of like we have a gradient between the two images. So from that gradient, we can then estimate where your region is going to be in the next frames.
And this is a tool that you may be familiar with already from the contour editor, where we've used that, or we still use it for electron microscopy images, and not only, but it works pretty well on EM data. Okay, that was the first question from Kaylee. There's a second question. How often do you press the train button when generating a pixel classifier? Only at the end or throughout your training process?
Well, there's a live preview, so if you have it on, you never have to touch the train button. It'll just generate the training and then apply with your current settings to, Luciano showed off the region of interest you can preview or the whole image. There is a parameter for the accuracy of the preview, so the preview is a preview. usually look to about what the end result is, but if you really want to see the end all, you have to teach and apply. But for the most part, the workflow is pretty straightforward. It'll just do it for you if you have it on. So
I typically don't teach all the time.
yeah,
I mean, I teach once I'm pretty happy with what the preview looks like. So often, yeah, I normally just the once. Okay, seems like Jeremy Cheng is happy with our answer. So is Alex. Kaylee, is there anything else that you might want to ask? Or anybody else? All right, seems like we're done. Thank you. Also in the room here is Sean and Bryce. They're kind of hiding over there, but they've also worked very hard on this release, as well as Quinn, who is checking out our live stream and making sure everything is working. All right, so I think we'll wrap it up. Thank you for joining.
yeah, thank you.
There's Quinn. Okay, thanks, bye.
Thank you.
Bye.